All right, guys, let's go ahead and get started. So to start off learning about Network Plus, it always starts at, the OSI model. How we encapsulate and de-encapsulate packets on a network. On a computer network, how does it go from computer at my source to a computer at the destination? And that is the de-encapsulation and re-encapsulation process. And we describe that de-encapsulation and re-encapsulation process with the OSI model. The OSI model is going to break that process down into 7 layers, starting at layer 1 through 7, or sometimes you start from layer 7 to 1, right? De-encapsulation, re-encapsulation. But we're going to go over each layer here and describe its purpose. So here's our exam objectives here that we're going to cover. So we're covering domain 1.1. We're going to go from layer 1 to layer 7. And first, let's go over the history of the OSI model. So just, I don't think this will be in the exam. They're not going to ask you what day did it come out, but just a little history. It was created in 1978, and it was published by ISO, the International Standards Organization, in 1980, which we still use today. ISO is still used. We have ISO standards that we use for some of our risk management frameworks in our networking or enterprises. So the OSI model is used to describe the different layers at which data communicates over computer systems. So just a little chart I made here, kind of going over the OSI model and how you would, the 7 layers here and what they're used for. So layers 1 through 7, we start at the physical layer. That's our physical structure, which means our data, when it's in binary, when it's in bits, how does it go across the network? What's our physical media? So that's going to be Wi-Fi. That's going to be copper and fiber, also hubs or repeaters. So that's always like a trick one. Like hubs, which was the predecessor to like a switch, is technically a layer 1 device, okay? Layer 2 is the data link layer, which is going to cover MAC addressing and what we call frames. So look at a layer 2 address that's encapsulating our data payload. We call that a frame. And in that layer 2 header is going to be source and destination MAC addresses. Switches are typically going to be the network device that switches layer 2 frames. And then a technology here, Ethernet, the 802.3 standard is in a layer 2 encapsulation standard. PPP is another old school layer 2 encapsulation standard. Layer 3, the network layer. As network engineers, we sometimes live in this layer 2 as well. But this is going to be our IP addressing. Now we're adding a layer 3 header onto our encapsulation, or encapsulating with the layer 3 header, and that's our source and destination IPs. So layer 3, the network layer, is all about IP addressing, IPv4, IPv6 addressing. This is how we get end-to-end communication. This is how we know where to send. Typically, the network device that deals with layer 3 is going to be routers. And when we call layer 3 encapsulated data, we call that a packet. So in that layer 3 header, we're going to have a source and destination IP address. And so, of course, the technologies is the Internet Protocol. That's V4 and V6. ICMP can kind of be considered like a layer 3 technology. Depends who you ask, but in this chart, that's what we're going to label it. And then IPsec, the IP Security Encapsulation Protocol. It's a VPN technology. That's layer 3. And then IGMP is also a layer 3 technology that deals with multicast. Layer 4, the transport layer. So this is going to deal with end-to-end reliability of our packets. So this is our end-to-end connections and our reliability. TCP and UDP is going to be the main transport layer technologies that we discuss. There's also something called QUIC that's not in here, but it's probably going to eventually be taught. But anyways, that's TCP and UDP. TCP being what's called the reliable communication method that ensures all packets reach its destination, and UDP being the unreliable layer 4 protocol that is just going to send and won't have any checksums, won't have any way to make sure that all data reaches to the destination. Okay? More on that later. Then we have layer 5, the session layer. This is going to manage the connection between endpoints, and that's going to be what's called sockets. So in here, that session layer, we're going to have sockets, we're going to do syncs, and this is going to be where our port lives, okay, our port numbers. Layer 6, the presentation layer. This is where we encode, encrypt, and compress data, and that deals with technologies like SSL, SSH, IMAP, JPEG, and PNG. So when I'm loading up a PNG file, that deals with the presentation layer. And then finally, layer 7, that's the application layer. That's what we call the end user layer. But really, what we're saying there, the application layer, is when I go access a website and I type in Hypertext Transfer Protocol, that's the application that's going to grab those HTML and CSS files from that web server and bring it to my web browser, which is my application, right? So that's the application layer. Okay, so more like some deep dives. So layer 1, the physical layer, this is going to handle the physical connection between devices. So again, I talked about this. This is our copper, which could be our UTP and STP, our unshielded and shielded twisted pairs. This could be coax cable that is going to send with electrical signals that then will get modulated at the end device, whatever that is, a computer to a switch, to send that binary. So it's analog coming across that layer 1. Now with fiber, that's going to also be analog, but it's going to be light. So instead of electrical diodes going back and forth over a copper cable, it's going to be a fiber and it's going to be light. We have two different modes of fiber. We have multi-mode and single mode, with multi-mode multiplexing light. So you can see it kind of scattering here. And the diameter of a multi-mode core is going to be 50 or 62.5 microns, okay? With single mode being a same thing, it's laser, it's light running through, but we're going to have a 9 micron center in that glass core, which is going to transmit that light. And single mode is going to be for long haul communication. So when I have a single mode cable, which typically is going to be like yellow, it's going to be a yellow fiber cable, that's going to be for 550 meters and above communication. Now with multi-mode, that's typically going to be with under 550 meters. It's going to be for short distances, talking data center racking and your LAN, okay? On that note, because I kind of skipped it, Cat 5 here, Cat 6, whatever you want to call it, we'll get into the standards. The untwisted pair, unshielded twisted pair, and the shielded twisted pair, up to Cat 6 is going to have a distance of 100 meters, okay? So copper is also going to be for those short distances in the data center in your LAN. Another layer 1 technology that sometimes we don't think about as layer 1 is actually Wi-Fi as well. So the RF signal that's going to radiate from the antennas on your wireless access points, that is layer 1. So when I have a Wi-Fi enabled device that connects to my access point over that wireless signal, I'm transmitting an RF signal and I'm receiving an RF signal from that access point, that is layer 1 as well, okay? Some other things on here we want to go over is a different standard. So when it comes to Ethernet standards, right here in this chart, we're going up to a gig, but it goes up to like 40 gig Ethernet. But when it comes to shielded or unshielded twisted pair, we can see our pinouts here, where when it comes to fast Ethernet speeds at 100 megabits per second, pins 1, 2 are transmitting and 3 and 6 are receiving. And then 4 and 5 and 7 and 8 are doing nothing unless you add power over Ethernet. Now, we deep dive into this a little bit more, so I'm just kind of glossing over, right? When we get up to gigabit Ethernet speeds, pins 1 through 8 are all going to be used to transmit and receive to get that higher data throughput. And all pins will also be used for that power over Ethernet. And then right here we have the different connector types for fiber. So we talk about connector types, like for unshielded and shielded twisted pair, we use RJ45 for our Cat 5, Cat 5e, Cat 6 standards. Here with fiber, we have like LC, SC, and I honestly forgetting what these are down here. But we have different connector types for fiber that can be used for single mode or multi-mode. Okay, the data link layer. So the data link layer, again, is going to be all about MAC addresses. It's going to be the 802.3 and 802.2 standard that is going to first encapsulate those data payload, okay? So leaving layer 1 into layer 2, we have the data link layer that is actually that Ethernet standard and how to encapsulate data, 802.3, 802.2. And this is going to do traffic control using MAC addressing, okay? So it's going to be source and destination MAC address. So the device that lives on our network that's going to forward layer 2 data frames is going to be a switch. So that switch out of the box is layer 2, and it's going to use MAC addressing to switch traffic from source to destination. It's going to switch that traffic based off destination MAC address. So it's going to have what's called a MAC address table that's going to be built based off ingress traffic. So when we have that layer 2 frame inbound from this server heading into gig 01 here. The switch is going to look at that layer 2 header and say, hey, that source MAC address I'm going to assign to this port, gig 00. And I'm going to look at your destination MAC address and see where you're trying to head. And if you're destined for this MAC address, BBBBB, I'm not going to say it all, I'm going to switch you out that port that it lives on. And I'm doing that by referencing that MAC address table. So switches make forwarding decisions based on the MAC address table, sometimes known as it's another name for it, CAM. The content addressable memory space is also what it's called. MAC address table and CAM table are the same thing. Okay, the network layer, or layer 3. So when it comes to layer 3, this is all about IP addressing. We put a layer 3 header, now encapsulating our layer 2 header with a source and destination IP address. That source IP is going to represent the sender, right? And the destination IP is wherever that sender wants to reach. So that is layer 3, IP addressing, the network layer. The devices that usually route layer 3 traffic are routers. But sometimes that can be a firewall that has routing functions, or it could be a multi-layer switch that has routing functions. A router or routing device is what forwards based off IP address. It does this by building an IP routing table. And in that routing table, it's going to build known routes with their destination. So if I learn about 1000, and I learned that via gig 00, and I have a packet inbound from one of my users that needs to go to that subnet, the destination IPs for that subnet, I'm going to send it out gig 00. That's how we route packets at a very broad level, right? I'm just going over the basics now. So layer 3 devices make the best forwarding decisions based on the best IP route in the routing table. So when we build that routing table, and we're learning about routes from all of our different routing neighbors, like these routers here, right? The New York router, learning from Phoenix and Australia router. If we learn about any duplicate routes, we're going to have routing protocols and different rules to select the best route to place in that routing table. But that is layer 3, the network layer, all about IP-based routing. And typically the device that does that is a router. But it can be a firewall or a switch or like an IDS, IPS appliance that may have routing capability. Okay, the transport layer. So I'm going to try to be not as long-winded here when it comes to the transport layer. And one second, guys. I'm going to grab my water so I don't lose my voice. One sec. Okay, I'm back. Okay, so layer 4, the transport layer. So this is about end-to-end reliability. Where layer 3 is where we send it, layer 4 is making sure that our entire data payload gets there. Or that it has that end-to-end communication from sender source to receiver or destination. Where like layer 3, right, the IP address kind of just says, hey, we know where that destination lives, but we're just, that's just we know where it's at. That doesn't involve the process of making sure that our data is fully going to get there. So layer 4, the transport layer, ensures reliable data transfer between systems. It does that flow control, it does error checking, and it does data segmentation. Now we have 2 protocols here though. So the 2 main protocols we use in layer 4 are going to be TCP and UDP. Where the transmission control protocol TCP is always going to be unicast, meaning one-to-one communication. Source to destination, sender to receiver, client to server. And it's also going to be reliable, meaning that we're going to do something called a 3-way handshake to establish a TCP data channel. And once that data channel is established, we'll start sending our data, and we're tracking to make sure that our data gets there completely. And if we do have packet loss or data loss, we're going to rebuild that channel again. In a later section, when I get into like TCP a little bit deeper, we'll go over kind of that flow. Where TCP pretty much, if you put it on a chart, let me bring up my pen app. Hold on. So I can kind of draw this out for you. With TCP, right, we have that 3-way handshake, of course. But, choose different color. But, after we do that handshake, and we establish that data channel, you can look at this on a chart where maybe, like, this is our throughput, 10, 15 megabits. This is all megabits, right? As we're sending data through that data channel, remember, this is like a server on this end, a client on this end. TCP's sending, we're sending, and if we notice packet loss at 10 megabits per second from source to destination, so remember, there could be a whole continent in between here full of routers routing traffic. The moment we notice packet loss, we dip down, we rebuild our data channel again, and then we start sending, okay? That's called TCP window scaling. So TCP, yes, it's reliable. Sometimes you don't get the best speeds. So imagine we're on a phone call or a video conference or we're live streaming and we had this kind of flow. Well, during a phone call, if there's a packet loss and you hear me say the, and I don't enunciate the, and then I continue speaking, that's okay, right? We don't want it to miss a single packet, then we drop our phone calls or we drop that live stream completely. It's okay if we miss a few packets and we rebuild or we resend that data, right? It's okay for some of our applications we use. So with UDP, you don't have any of this. With UDP, we're just going to send and forget. We're going to just keep sending our traffic. And when I say forget, obviously we have refragmentation where we're going to say, hey, like we may need to keep sending traffic to get there, but it's not going to drop just because we have a single packet loss or a single kilobyte or a single byte of packet loss, okay? Where with TCP, we will. We want to make sure we're getting every single data packet. So with things like HTTP, HTTPS, we're going to like a blog. Imagine if we use UDP to get to a blog. Said, hey, we made that connection, send the traffic. We missed some data, and I'm missing now a whole paragraph in that blog. Well, we don't want that, right? We want TCP for that because we want end-to-end reliability. I want to get that entire packet. Well, if we're on a phone call, it's okay if we got some packet loss. Hey, just repeat what you said again, and we don't drop that connection, right? And then with UDP, we're unicast or one-to-one. We're broadcast, which is one-to-all. Or we're multicast, which is one-to-many. So all of our multicast streams always be one-to-many. We have to actually subscribe to that multicast IP address to listen, and that's going to be UDP. Or broadcast will always be UDP as well. Okay, now layer 5, the session layer. So with that session layer, this is going to establish, manage, and terminate sessions between two communicating devices, and it's going to control the dialogue between devices. So imagine this like our TLS session, okay? So when we're doing TLS, without getting into the cryptography behind it, you know, our router or whatever, from client to server is really a better way to describe it. We're going to build that TLS session there. That's layer 5. That's that session layer. We have session establishment, synchronization, and checkpointing, okay? So the TCP flow is also a part of this. The initial connection, though, is layer 4, but TLS is a great way to describe layer 5, the session layer. So like in video conferencing, the session layer is responsible for setting up and managing the session and ensuring that the video and audio streams remain in sync. Okay, layer 6, the presentation layer. So this translates data between the application layer and the network, ensuring that the data is in a usable format. So this is like data encoding. So when I gotta turn plain text into binary, into ciphertext, this is part of the presentation layer. If I gotta translate characters into ASCII so it can be human readable, that's part of the presentation layer. Data encryption and decryption, that's at the presentation layer when it actually hits your computer, right? So like a real world example, when transferring files over the internet, the presentation layer may compress the files to reduce transfer time and encrypt them to protect against unauthorized access. So when I'm doing like data at rest, right, and I'm encrypting, doing full disk encryption, that's technically the presentation layer. If I need to zip a folder and then encrypt it and then send it, that's part of the presentation layer. Now you may say, well, you just said TLS does encryption at layer 5. That's true. That's data in transit. Here it's more about data at rest when you actually receive the file. So let's say I get a transfer, I get a zip file, and at my desktop I need to put in a password to decrypt it and then unzip it. That's the presentation layer. More at the user, the client level. Okay, then layer 7, the application layer. Kind of, for like a newbie in networking, kind of easy to understand, but also a little confusing because like HTTP, which is something you may need to troubleshoot to make sure HTTP is working on your network, it's port 443, is actually an application though. The hypertext transfer protocol is an actual application that somebody coded and created. And it's something that as users we use every day. I mean, I'm literally on camera right now and I'm accessing this web application via the hypertext transfer protocol. So the application layer provides network services directly to end user application. It's the layer where users interact with the network and provides services such as email, file transfer, and web browsing. So some key applications that we may troubleshoot as network engineers It's going to be like HTTP, FTP, SMTP, pretty much any of those like protocols that are enterprise things, right? Like SMTP is for email. Our users need to access web portals, so HTTP. They need to do file transfer, so FTP, or like SMB or NFS for like our local file shares, right? Things like LDAP, Lightweight Directory Access Protocol. That's all like an application that we may need to help manage on the network to make sure it's reachable. We're not blocking it on ACLs or things like that. Okay. All right. Now let's do our quiz. So remember, this is domain 1.1.1. So if you're in our lessons right here, domain 1.1.1, you could take domain quiz here. Okay. I know that went super fast, but on our LMS, if you go to your lessons, domain 1.1.1, that's where the quiz is going to be. It'll also be in that quizzes section. But okay, let's do it. Let me bring up something on my side real quick. One second, guys. Okay, so question 1. Which OSI layer is primarily concerned with ensuring that data is transmitted error-free and in the correct sequence between devices? So which OSI layer is primarily concerned with ensuring that data is transmitted error-free and in the correct sequence? So correct sequence, that's like our flow control, our data flow control. So I'm going to go with the transport layers. That's our TCP and UDP protocols. And you can look at the explanation here. Okay, question 2. Which layer of the OSI model is responsible for determining the path that data will take from the source to destination across multiple networks? So just off rip here, I'm going to say this is probably like layer 3 because this is across multiple networks. So like a router would be doing that, right? A router would be making sure that a packet from the source to destination can reach. So I'm going to go with the network layer. Question 3. Which layer of the OSI model is responsible for translating data formats and handling encryption and decryption to ensure that data is in a usable format? So data is in a usable format between encryption, decryption. So that's going to be on the client side, really, right? Kind of what we just talked about, where if I zip a folder and encrypt it and send it to you, or if you ever gotten like an encrypted PDF and then, you have to unencrypt it, that's going to be the presentation layer. Okay, question 4. In which layer of the OSI model does the process of session management, including the establishment, maintenance, and termination of connections, occur? So session management, right? That's probably going to be the session layer. Let's see. Yeah, let's go with session layer. So yep, that'll be layer 5. Okay, question 5. At which layer of the OSI model would you find devices such as switches and techniques like MAC address filtering? So that's the data link layer, right? Data link layer equals layer 2 equals MAC addresses equals switches. Okay, last question in our quiz here. If you were troubleshooting a problem where devices on the local network could not communicate with each other, which OSI layer would you likely begin with? So kind of like troubleshooting, right? Like, hey, where would you begin troubleshooting? That's how I read this. And when you're dealing with users on an enterprise, it's always the physical layer, right? We always start at layer 1. Just make sure things are plugged in correctly. And even if you're working in data centers or like network and like NOC environments, layer 1 sometimes, is the issue a lot of the times. All right. So we got 100%. Sweet. I'm going to take a little break here, guys, to get my voice a rest. So it is 6:41 East Coast time. Let's come back at 6:50 p.m. and then we'll get started going over domain 1.2. All right, guys, let's go ahead and get started again. So now we're going to go over domain 1.2, which is networking appliances, applications, and functions. So we're going to go over physical and virtual appliances in the network. So obviously our physical appliances, routers, switches, firewalls. Actually, a lot of this can also be virtualized. It's called NFV, Network Functions Virtualization. But we're going to go over these physical appliances and some that can be virtualized. We're going to go over different applications you may see on your network. A CDN, like content delivery network. Yeah, it has network in the name, but really that's like if you're building a web server and you want to distribute your content to different geographical regions, use CDN. It's really easy to configure though. Like on most like cloud environments, you just kind of like enable it. But it can be more complex depending. And then different functions. So go over VPN, quality of service, and what a time to live is in an IP-based packet. Okay, so a router. This is, again, a network device that forwards packets based on their IP address and is responsible for data reaching its network. So typically, I have a Cisco background. So when I think routing, I think Cisco ISR, ASRs, but there's other routers out there in the world as well. I've configured Unify routers, and they all pretty much have the same basic premise. Take your source traffic, your users, and get them to their destination. Now, some routers can have additional functionality in there. Like my Unify router, what they call their like cloud gateway, we have firewall functionality in there. We have VPN functionality in there. We also have a layer 2 switch as part of that router. So at its base level, though, a router builds a routing table that stores all known IP routes and that is the brain of the router. We're going to have all the best known destination. So out of the box, routers are layer 3 and perform basic IP routing forwarding functions. But if properly licensed and if you have paid for extra features, like a Cisco ISR integrated service router, there is that additional functionality like I talked about. Okay, switch. So this is a network device that forwards data, packets, or frames locally within a LAN or a switch domain, like your broadcast domain. So let's actually jump into a switch here. Let me bring up secure CRT. Let me bring it over here. And let's actually go in to a network device here. So this is going to be a Catalyst 9300 device. This is a Cisco switch. What's going on? Password, Cisco. Okay. This is just a local switch in my office. So if you're like, oh, you just said the password out loud, like it's okay. I break this thing all the time and reboot it all the time. So this is my office switch here. So this is the Cisco CLI. No, this might not be testable per se, but I just want to show you some commands here. So we have show MAC address table. So show MAC address table is going to show us all the learned MAC addresses. Here it's going to show us the VLAN they're in, and then what interface they're learned off of. So you can see here that port 45, and then also, well, actually port 42 here too, is learning multiple MAC addresses. So more than likely this may be like a trunk port, right? Port 42 here. So we could type in show run interface gig 60/42. And nope, that's not a trunk. Let's look at 45. But that's a trunk because we're learning multiple MAC addresses off it. Port 42 more than likely is going to be an access point. So if you ever see multiple MAC addresses coming in on an interface and it's not a trunk, more than likely it's an access point, and that's my Unify access point here. If we do show LLDP neighbors, you can see that U6 light, that's an access point, okay? So you can see a switch here, it's all MAC addresses. This port ID is all MAC addressing. When I type in show MAC address table, this is the brain of the switch, how we're forwarding traffic. So if I have this MAC address coming in on gig 42 here, and it wants to talk to this MAC address here, it lives on gig 43, the switch will switch that traffic, okay? Now let's get back to our slides here. And then, of course, a switch also, out of the box is layer 2, but it can do routing as well. It can be a multi-layer switch is what we call it. Okay. And if you're wondering how we do that too, so sometimes I like to get a little hands-on. Like in a Cisco switch, first we have the command IP routing, which enables, hey, we're going to have a routing table. So if I now type in do show IP route, here's our routing table. There's not a lot going on here. but we can also make our switch ports, because all the ports on a switch are technically out of the box layer 2. So we call them switch ports, layer 2 ports. But we could, if we wanted to, go in and say no switch port, and now we can put an IP address on there. So we can put a IP address on there. But if I try to do that on a regular switch port, IP address, it's not going to let me. It's going to say invalid input because it's layer 2 right now out of the box until I make it a layer 3, okay? All right, back to our lab, or back to our presentation. Firewalls. So this is a network device that by default, like a base firewall, it filters packets. It's going to have inside zones, outside zones, trust levels, and it's going to have access control lists, filtering traffic inbound and outbound. That's at its base level what a firewall does. Now, how it does that, the nitty gritty. We could have stateful or stateless firewalls. We could have firewalls that filter based off destination IP, ports, and protocols. We could have next generation firewalls, more advanced, that are application aware, that are doing TLS inspection. So that's decrypting and encrypting TLS sessions to look at that client to web server connection. We could have URL filtering on firewalls, context aware, which is kind of just what I described, just different, words to say it. But at its base level, it's there to filter packets inbound and outbound. That's what a firewall is there for. We have physical appliances for firewalls. So a firewall that sits in your data center that maybe sits in line on your network. We also have cloud-based firewalls that do pretty much the same thing. So if I go to my Azure portal here, let's look at what a firewall would be in the Azure portal. So let me take a second to log in. I should have done this in the break. Oh, okay, we're already there. Cool. What? This random IP. Let's just do this one. Or an email address. See that? They try to market me. In the Azure portal, they tried to market me. It's crazy. So, in Azure, if we look up firewalls, we have software-defined firewalls here, where we can create a firewall, and we can attach that to like a virtual network. So it's attaching it to like a subnet. Here's where you're going to do your filtering. And then we place resources in that VNet or in that subnet. And that could do our filtering. We also have things like NSGs, network security groups, that also have filtering functions. So firewalls can be that hard physical appliance that sits in line on our network, or it could be in the cloud. It could be something virtual. We have firewall switches and routers in our virtualized data centers as well. So if we're in a VMware environment, we could have routing, vSwitches, and even virtual firewalls. In our Linux devices, we could have something like UFW, which is kind of like old school, but we could have IP tables. We could have firewall functions on our Linux servers as well. Where did my slides go? Right here. All right. Okay, IDS and IPS. So intrusion detection, intrusion prevention systems. So IDS and IPS have similar functions, but there's one critical distinction, where IPS stands for intrusion prevention system, IDS stands for intrusion detection system. So at the base level, they're inspecting traffic. They're always going to be inspecting traffic. But with the IDS system, we're looking for vulnerabilities coming across our network, and we're alerting our administrators. We're alerting them. So we're putting in rules, we're putting in notification levels, notification rules in our IDS systems to alert us, to send us a notification on whatever our systems are. If that's a Slack message, an email, a Teams message, a phone call even, whatever the case may be. With the IPS system, you can do the same thing. You can set up alerts, detect network anomalies, things that deviate from the baseline, but you have a little bit extra functionality where you can actually go and prevent something. Now you can block traffic, which can be a good thing for proactive remediation, but could also be a bad thing because maybe it may block something that's legitimate that the system thinks is illegitimate because we didn't put in the proper signatures, rules, or enable a good ML AI language in there, a large learning model, okay? A load balancer. This is another network appliance that could be virtual, it could be physical. If we look at Microsoft Azure, we have load balancers here that sit just outside our virtual network that can load balance between different VNets within the same region, or not even that, we could load balance between different architectures and devices in Azure. Not architectures, different devices within Azure, okay? So we could have like a web server farm here. We could have a cluster, a Kubernetes cluster here, and a load balancer on there that's load balancing the inbound connections, okay? Cool. So the point of a load balancer is to increase availability for our network so we don't get like throttled on a single path. It's also for redundancy as well. A load balancer could be there to give you redundancy. A load balancer also has something called a virtual IP, where if we look at just this little diagram we have here, this load balancer is going to have a virtual IP that sits here. That'll be .1. So this would be like the 192.168.0.1 network /24. And this web server farm may be servicing all the same customers. So we could have like index.html 1 here, and then HTML/2, HTML/3 here. And they're serving up files for any request, right? So this is a web server farm that creates what looks like the single web application or single URL to you, the user, right? But on the back end, we can have something like this. So what this load balancer does, it's going to represent a single web server using this virtual IP. And all these servers are going to talk to this one virtual IP. And our users out here, they connect to the internet. We have a public IP there, which is going to be, the public IP is what we actually connect to. So our A record, like in our DNS settings, will be this public IP. But on the back end, we have this virtual IP that's actually going to be doing the traffic loads, the traffic sharing, and the network connections. So a load balancer could be doing a lot more than just, distributing loads. It could be also doing network address translation, which we're going to talk about. So this load balancer gives us a lot. It gives us scalability, availability, redundancy, the ability to distribute traffic, but also gives us some protections, right? It's almost acting like a proxy. You connect to this public IP, but behind here I have my web servers that are on these private IPs that you can't directly connect to. Okay, I am being a little long-winded. Let's move on. Okay, I have proxy. So a proxy server is going to act as an intermediary between end users and the internet. Now we have two different ways we can deploy a proxy, reverse or forward. With the forward proxy, that's going to sit on our enterprise here, and our users are going to connect to that before going out to the internet. So our users connect to this proxy when they're doing internet connections. Now, again, there's going to be a router in here. It's probably not our default gateway, but that forward proxy will get that traffic and say, before you leave the internet, what I'm going to do is I'm going to translate you to this, and I'm also going to inspect you, because this may be like an F5 load balancer proxy that we also might put some IPS rules in here, right? Some URL filtering. So a lot of times these appliances have dual functions, but for the Network Plus exam, just know that a proxy is going to mask the IP address of users or your servers, okay? But it also can do content filtering. It also has the ability to cache, so it can cache some of these front-end files in here. So if it's a website that you're constantly going to, I get comments on my handwriting is shit all the time. Let me rewrite this. I need to write better. Hold on, let me change the size here. It helps me. So I could be caching like front-end stuff here, right? So if I'm always going to like whatever this web server is, I can cache some of that here at the actual proxy. Now, reverse proxy does essentially the same thing. It masks IP addresses, but for the web server farm. It's kind of like that load balancer did, right? Where you think you're going to, let's say, example.com here, and you think, that's a single IP address, but really you're connecting to 12.3.3.2, and then this proxy is distributing those connections out, okay? It's just doing that, right? But that's what a reverse proxy is. It sits on the web server side, not on your enterprise. So you can kind of think of reverse proxy, that would sit in the cloud or the data center, where the forward proxy would sit local on the enterprise. Okay? Okay, network attached storage. So when you have like a spoke office, let's say you have your headquarters in New York, but you're in a spoke office in like San Antonio, Texas, and you need some place to locally store things that you're doing at that spoke office. So you don't need something robust, but you need something. Well, that's where network attached storage comes in. So NAS, or network attached storage, is a file level storage device connected to a network that uses things like NFS, SMB, that allows you to create file shares. That's it. Just local, and it's not robust, and it's file level storage. So it provides that centralized location for storing and sharing files. Big thing to note here, right? Network Plus exam we're trying to pass. NAS is not robust enterprise level storage. It's local, it's small, it's for that spoke office, small office, home office, okay? And it's a device that's going to go directly into like an access switch, okay? Little 24-port, 8-port switch that sits in your little comms closet in your spoke office. That's where that is. Like, if I had network attached storage in my office, it would be in my little rack right here. And that would be it. Just directly attached to my access switch there, okay? But its counterpart, or what you use in robust enterprises that require block level storage with petabytes, that storage area network. So a SAN is really like an entire job field too, like a storage SAN administrator. That's a high-speed network that provides block level storage to multiple servers. So you ever seen like a data center build where you'll have your rack, right? So in that rack, you may have like power, so you have your ups. And then you'll have here, which looks like just rows and rows and blades of drives, hard drives. That's storage area network. And on the back end, you may have like TwinAx, you may have iSCSI, fiber channel over Ethernet. You have like 40 gig connections here. Where does that plug into? Well, it's probably going to plug into like either a network switch, like a Nexus switch or something like that, or some sort of robust enterprise, a data center level switch. But then also whatever your compute is. So here, let's say you have like a Cisco UCS chassis, and this is like where your compute lives. When I say compute, I mean like your VMs, right? And where do all those VM files? Where's your data store at? Where's all the storage for your VMs? It's going to be located in that SAN, right? So it's that robust level raw block storage that we provide to the enterprise, but also to like our data center components as well. So our compute right here, where our VMs live, their data stores and their storage will actually live on this SAN, that robust block level storage. And yes, sometimes you're dealing with, hundreds of terabytes or even like petabytes here, okay? In the modern large enterprise that's doing all local storage, not, buckets in the cloud. That's SAN, okay? High performance too. So looking at some of those key features here for the exam. Okay, let me erase this writing. Okay, access points. So this is the network device this is the device that sends out a Wi-Fi signal that connects to Wi-Fi enabled devices, that connects you back to the backbone or the switched network to give you network access. So Wi-Fi is the 802.11 standard. That's what emits from these access points, these wireless access points. And there's going to be different Wi-Fi speeds and standards that we also talk about. Right now, we're actually up to Wi-Fi 7, but in the Network Plus exam, it caps out at Wi-Fi 6 or 802.11x, which we'll get to. Access points also, a common mistake people believe about access points is that they represent that when an access point broadcasts a network, it's going to broadcast an SSID. So if I come up here to my MacBook and I look up here, I look up all these networks. These are all service set identifiers that are identifying different networks you can connect to. So a lot of times people believe that an SSID represents a single access point. That's wrong. An SSID represents a network. So yes, an access point here could actually be broadcasting this SSID, this SSID, and this SSID. And these two SSIDs can belong to this subnet, 10.0. And that could be like VLAN 10 on your backbone on your switches. And then this could be 192.168.5.0. And this could be like VLAN 5. So an access point can broadcast multiple SSIDs, which correspond to a wireless local area network, or a network, okay? An SSID doesn't represent a single access point. Then we also have security, called Wi-Fi protected access, 2 and 3, that we'll get to. We're not going to dive too deep into that. Let me bring my pen over here so I can be a little bit quicker. Okay, a wireless controller. So sometimes you're in a large enterprise, think of hospital, think of airports, stadiums, office buildings that you have 24 floors you have to manage. And you all have Wi-Fi. You'll have Wi-Fi enabled devices. So that means you have thousands of access points emitting Wi-Fi signals to have full coverage. And you got to have advanced features on there like 802.1x, network access control, quality of service, be able to rotate between different channels, channel bonding, 802.11r, which is roaming, extended SSIDs. I could go on and on. So in that kind of robust environment with thousands of access points, we need a wireless controller that's going to be the centralized place to manage all these access points in a uniformed way, to give you that single pane of glass to manage all your access points. So for the Network Plus exam, to tie this all up, a wireless controller manages multiple wireless access points. And that's as deep as we're going to get. I don't know if you can see, but I really like to dive deep into wireless. But again, we're here, broad strokes, Network Plus exam, okay? All right, let's do our quiz now. Let me come here. So we are in domain 1.2.1. So I can come to my quizzes and search here, domain 1.2.1. And let's do this quiz. And I'm going to take another little break to rest my voice. Let me bring something up over here. 1 second. Stateful firewall. Okay. What does a stateful firewall primarily do? I don't think I covered what stateful actually does, so this is a good thing we are doing our quiz. So a stateful firewall, since I didn't go over it, I'll just explain it right here. It tracks the state of active connections and makes decisions based on the context of the traffic. So this is like if you're connecting to a server, so you're coming from inside the network and your firewall is tracking that, it's going to trust that connection, okay? So that's a stateful firewall. Read the explanation if you'd like as well. Question 2. Which of the following features is commonly associated with a network switch? So a switch does VLAN support, right? So that's our virtual local area networks. So VLANs are going to correlate to different broadcast domains all within your geographical LAN, okay? We're going to get to that a little bit more in depth. I should have went over that in the slides, but yes, VLAN support. Question 3. Which statement best describes the difference between an IDS and an IPS? Remember, IDS and IPS, they track traffic. They're inspecting traffic, but one detects, one prevents. So one's for alerting and monitoring only. One can alert, monitor, detect, and also block traffic, prevent traffic. So an IDS monitors and alerts, while IPS can take direct action to block. I'm not even going to read the rest because that's it right there, A. So an IDS monitors and alerts, while an IPS can take direct action to block threats. What just happened? Hold on. All right. 1 second here. I hit back and messed it all up. All right, let's continue. See, it tracks our progress. Okay. All right, question 4. What is the primary function of a router in a network? That's to route IP-based traffic. So let's take a look at our answers here. To monitor and filter, To provide wireless connectivity, To connect multiple networks and route data between them, I think that's going to be our answer. So we're going to go with B. Question 5. What is the main purpose of a load balancer in a network? So that's our redundancy, our availability to distribute those incoming TCP connections to all of our web servers. That's going to be D, to distribute incoming network traffic across multiple servers. All right, let's go. That is 100% right there. Let's take another break, guys. Sorry, it's day 1. I got to warm up my voice. So let's take another 10-minute break. Let's come back at 7:25. 7:25. All right, guys, let's go ahead and get started again. So now we're going to go over domain 1.2.2, networking appliances, applications, and functions. But now we're actually going to get into the applications and functions. So first thing I want to talk about is the content delivery network. So like I kind of already talked about, imagine we have a website, a blog. Well, it's kind of like about the local area, but then we start taking off. Or whatever kind of website we have, now we have a global audience. Well, our little server that we're renting out in California, VPS for $16.99 a month, is all the compute, storage, memory, RAM, and network we need because we have a lightweight site. But we noticed that users in Australia complain about lag or complain about just the availability of it. It's not very fast. So what we can do is create something called a CDN, a content delivery network. So this is a network of distributed servers that work together to deliver front-end content, web pages, images, and videos. So something that's front-end. This is not going to be distributing SQL databases across the globe, right? This is like our front-end things that our web pages call upon to give us our front-end display. So if you need a network appliance that allows you to distribute, if you need a network appliance that allows you to bring your content globally, that's going to be a CDN. Kind of trying to think of how they would ask you a question in Network Plus. Then a VPN. So we actually deep dive into VPNs later on as well, and the genesis of VPNs is actually a really fun topic that I'm going to try to keep at surface level. When VPNs were first created, it was really just a way to connect geographically dispersed offices together, to directly connect them. Because back in the day when you had an enterprise, so I had my headquarters in California, and I had offices in Phoenix, offices in Sacramento, and I was headquartered in Los Angeles. If I wanted my little data center I had in my headquarters for my users in Arizona, I used to have to buy a dedicated link. Like a dedicated copper line. This was before MPLS, Layer 3 VPN. This was like frame relay talking kind of stuff. And you have to buy that direct link from the ISP that said, I need a direct connection from this office to my headquarters here. And that would cost a lot. So VPNs were created as a technology to say, actually, let's just use the internet as our, use the internet and a VPN connection to directly connect our devices. We'll use the internet to send that traffic. And what we'll do is we'll encapsulate our traffic to hide it from the internet, to hide it from that unsafe area. That was the original genesis of VPNs, to give ourselves like IP address masking to connect geographically distant sites. Now, in modern day VPNs, they do a lot. So VPNs give us data in transit encryption. It still gives us that IP address masking. It gives us the ability to do secure remote access. If we have remote users, they connect via Cisco AnyConnect VPN client from their home to get into our enterprise to access our share portals. And it also does, of course, have geo restrictions. If I want to go watch a show in London, I put a VPN on. It doesn't really work now. Most streaming services kind of like block that. They recognize that a proxy is being used. Because remember, proxy, VPN, it does IP address masking. That's the genesis of it. You have your original layer 3 IP header. A VPN puts another one on there to change it. But that's its functions. Now, in the Network Plus exam, right? This is an exam that's getting you ready to be a network administrator or engineer. So that original use case for VPNs, we're still going to talk about. It's that site-to-site VPN. And then, of course, in our modern day architectures, we have hybrid and remote workers. We have on-site workers. And the boss still wants you to connect to Teams on your way home. Anyways, you still need to know another use case of it, kind of more modern, is that remote access VPN. We have a VPN on a user's personal laptop or computer to connect you to the enterprise. Those are two different types, site-to-site and remote access VPN. Okay, I think I just made this slide to give you like a more in-depth. You see here, like our remote access VPN. Here we have our remote worker. Just connected to any ISP, right? This is like a coffee shop. They turn on their VPN. That's going to connect to whatever VPN concentrator they have at the enterprise. That could just be a firewall. It could just be a router. It could be a dedicated appliance too. It could also be in the cloud as well, depending on how your enterprise sits. But you connect there, and now you're able to access your enterprise resources that could not be accessed via just regular internet connection. Then, of course, our site-to-site is when we have these network devices creating VPNs to each other. So this is network devices, router to router, router to firewall, firewall to firewall, VPN concentrator. That's not typical at all, but that's network devices actually connecting to each other. Then within those two major types, we talk about site to site and remote access. So those are the two major kind of way you architecture VPNs. And with site to site VPN, that's going to be like your IPsec GRE technologies or like MPLS layer 3 VPN. But with remote access, that's going to be like a SSL, TLS VPN, things like WireGuard. But there's also different ways we build the VPN for network traffic. So let's talk about this. So we have, within those two major types, site-to-site and remote access, we have different ways to configure them. Split tunnel or full tunnel. So imagine this. So imagine you're a remote access user, okay? So you're sitting at home and you're connected to your ISP here. And your work says, hey, you want to work remote? Dope. You can use your own computer. Or we're going to send you home with a development computer. Big, beefy computer. You can use it for whatever you want, but that's your work computer. So they say they install a VPN client, right? Whether they're using a mobile device management solution, they put a VPN client on there. So when you go to work, you activate that VPN. If it's configured as full tunnel, all traffic, even if you're going to youtube.com, all traffic's going to go through that VPN, meaning that all traffic's going to hit your enterprise network, whatever VPN concentrator they have there, and then that router's going to route it. So your VPN connects to some sort of VPN concentrator, router, firewall, whatever it is, and it's going to say, hey, oh, you're trying to access the enterprise? Cool. Access our data center. Oh, you're trying to go to YouTube? Cool. I'm going to send you out to the internet, YouTube. That's full tunnel. Now, you may say, why would we want that, right? If the VPN's on our computer so we can access our enterprise network, wouldn't we just want to use the VPN just when we're accessing enterprise networks? And I would agree with you. There is a use case for this. Sometimes security, compliance, weird things going on. But what I like to see in remote access, and, well, actually, it doesn't matter what I like. This is CompTIA. We're just going to learn about it, is a split tunnel. With a split tunnel VPN, this is going to go on your computer and it's going to say, hey, computer, our enterprise network is this subnet. So anytime you get a request to go to an IP address that falls within that subnet, go out the VPN. Any other traffic that's not destined to our enterprise subnet, use your regular internet connection. That's a split tunnel. So when I build WireGuard VPNs from my office to like computers that travel, because I have like traveling instructors, that's what I do. I build split tunnels so that when they activate it, because they need to access resources in my office that I'm hosting here for the in-person classes, they can access it, but then their regular internet connections go out to the internet. And I prefer that. Okay. QoS. Man, I have a 3 to 4 hour video series on QoS, my CCNA videos. This is something I like to deep dive into, but I'm not going to. Because for the Network Plus QoS, you need to know one thing. It's to help shape and prioritize network traffic, and it helps with bandwidth management. It helps shape and prioritize traffic, does bandwidth management, and it reduces this. So you don't have latency, you don't have jitter, and you don't have drop packets. Essentially, just imagine QoS. You need to apply it once your pipe is full. You know, this 100 megabit pipe is full. You need to start applying QoS to prioritize the traffic that's going to get that pipe. Okay? That's QoS. And that's as hurts me, but that's as far as I'm going to go. Okay? TTL. So time to live. This is within the actual IP header. It's called a hop limit. Starts at 255, and at every hop it goes down, and if you get down to 0, it drops traffic. That's it. That's all TTL does, okay? So it starts at 255, at every hop it goes down by 1, and if you get down to 0, whatever router gets that traffic, it's like, oh, the TTL's at 1, I can't send it anymore. That's it. That's the time to live, okay? Let's do a quiz. I'm trying to get through 2 sections before I need another break. Okay, so we're at domain 1.2.2. Let's go to these quizzes. And yeah, I'm fully zoomed in on mine, so that's why it looks like this. Or I'm zoomed in a lot. Okay, question 1. What is the main goal of implementing quality of service in a network? That's going to be B. So remember, it's just priorities. Prioritizing traffic to ensure critical network traffic receives priority over less important traffic. So if we start filling up our bandwidth, our pipe is full, it's bursting, right? And we say, whoa, what's critical applications? So what's the critical applications we need to conduct business? This all depends on your enterprise. But if we're making deals, we have salesmen, we have marketers that need to access social media, and we have salespeople that need be on their cell phones or their phones making calls, sending emails. That's your priority right there. YouTube, everything else, every other top bandwidth talker gets pushed to the side with QoS, right? That's its goal. Question 2. What is the primary purpose of a content delivery network? So this is going to be, you guessed it, to deliver content, the front-end content for websites like web pages, images, and videos based on the geographic location. You know, we have a global audience. We don't want them to have high latency, so we deploy a CDN. Question 3. Which of the following is a key function of a virtual private network? Doesn't distribute traffic, doesn't prioritize, doesn't care about hops, that's TTL. So one of the key functions is encrypting data. And I say that because, like, obviously with MPLS, like if you ever worked ISP side, you know, major enterprise, MPLS layer 3 VPNs, inherently they're not encrypted, right? So VPNs don't have to have encryption, but yes, for the Network Plus exam as a network administrator, when you're deploying site to site, remote access VPN, it's always going to have some sort of protection on it. So we'll go with A. Okay, question 4. The time to live TTL field in an IP packet is primarily used for which purpose? So that is to specify the maximum number of hops a packet can take before being discarded. Remember, 255 is its start. So if it gets down to 0, boop, that thing is gone. That packet is out of here. All right, awesome. Another 100%. We're killing it, guys. We are killing it. Let me bring up our next lesson. Where is, hold on, Canva. 1 second. I use Canva to make my slides, and I closed out of it over on my other monitor. Just give me 1 second while I bring up domain 1.3.1. Oh yeah, we're going over the cloud. Awesome. I love talking about the cloud. I'm going to try not to be too long-winded though. Then we'll see what we get, and then maybe I'll take another break. Okay, domain 1.3.1. Summarize cloud concepts and connectivity options. So we're going to go over the basics of clouds, and then some of these other, I wouldn't call them advanced stuff, just like other little like cloud technologies, options, features, applications we have, okay? But the deployment, service models, and then, you know, the pay-as-you-go, scalable, elastic model is like pretty much like the fundamentals of the cloud, okay? Now, I can't help it. Let's bring up a whiteboard for this. This is important because pretty much if you look at network engineering jobs now, if you're not, I work in the DoD, so I mean, this doesn't always apply to my sector, but I mean, every network engineering job now, it's almost like they want one of two things, either automation experience or some sort of cloud experience with networking. So this is important. Let's bring up a whiteboard. Let me bring up a whiteboard. Hold on. Okay. So when we talk about the cloud, right? Let me get this out of the way. When we talk about the cloud, really, it's important to understand why we moved to the cloud. So I'm going to try to keep this as simple as possible. So when we had enterprises, we had data centers, local on-prem data centers. And remember, what do those data centers have? So we had power. I'm not going to write that. But our data centers gave us storage utility. It gave us compute resources. Remember, compute is our VM, so that's, you know, our SharePoint portals, print servers, domain controllers, DHCP servers, DNS servers. And then, of course, our network. And that's our like switches and routers that were able to route the traffic to us and out to the internet. So when I went and bought the hardware for storage, bought the hardware for compute, I like to draw like Cisco UCS chassis. You ever see them? That's how I like look at them. And you had to go buy the network hardware. All of this was called a capital expense, CapEx. So essentially, we had to buy the upfront hardware, and what we bought is what we were stuck with. So if this compute resource had, I don't know, 1,024 gigs of RAM, and my storage had 500 terabytes, and we filled out all the slots for the drives. Then my network was only 10 gigabit Ethernet, right, for speeds. That's all we had. So we had a cost here. We had to get a vendor, end of life. We had to worry about all this kind of stuff, an upfront cost. And then we had a maintenance cost. And then we had to get a SAN administrator, right? A SAN guy. We had to buy a system administrator. And we also had to get a network engineer. I'm just going to put network engineer here. So we had all these costs, right? And then let's say we're hosting e-commerce. We're I don't know, e-commerce with that much compute, but let's just say we host e-commerce. And so for 10 months out of the year, we only use 50% of our compute resources. But then for those 2 months during Christmas, we're using 110%. Meaning we're actually getting some issues, network latencies, websites going down, and we're like, fuck, we got to add more compute. So then what do we got to do? We got to go buy another server, see how to cluster it. We have a lot of downtime, and our scalability and elasticity kind of suffers. So the business solution to this was the cloud. Where the cloud is not an upfront cost, it's called an operational expense. With the cloud, one of the 5 tenets as described by the NIST standard of what cloud computing is you had high scalability, which can go up and down with a touch, right? With how you provision is quick. Provisioning, deprovisioning is quick. And with that, you had elasticity. And when you connected to the cloud, all you needed was internet access. So you didn't have to configure any VPNs, anything fancy to get you access from your home into your data center. With the cloud, you just need access to the internet. These are some of the main tenets of the cloud, okay? So now with that, when cloud architecture started being developed, we just had different models and different deployment models and different service models of the cloud. So the cloud aimed to take everything we were doing in the data center and to put it in a single cloud-based portal that you can access that gave you all this functionality, storage, compute, and network that you can deliver still to your enterprise, but you can do it at cost with kind of like a pay-as-you-go model. So deploying VMs in EXXI, I can now do it in the cloud, and I can scale those VMs up, but it's going to cost me an hourly rate, right? And that can sometimes save you money. So now let's get into the different models. So with that, we came up with different models. So the first model was the public cloud. We talk about deployment models. First was the public cloud. So the public cloud, this was a multi-tenant environment. So what do I mean by multi-tenant? It's shared, meaning that if me and you sign up for Azure and we put a VM in the East region, like Virginia, US East 1, we could possibly have our data on the same server. So it's that multi-tenant environment. The public cloud, we all access the portal. Now our portal may be unique to us. We have protections to our portal using like identity access management, right? Like access control. But when I'm deploying a storage account, I'm deploying a VNet, I'm deploying VMs, compute resources, storage, Azure Blob Storage, our data could potentially be in the same servers in that same cloud data center. So that's the public cloud. And then we had the private cloud. So the private cloud is something you develop. So that's you, again, taking this data center model and saying, I'm going to scale out my data centers to be comparable to a cloud data center. And it's just going to be for us, just our enterprise. That's it. So giving us access to a cloud-like data center that's just for us. It's not multi-tenant, it's just for us. This could also be like the Gov cloud. That could be considered a private cloud. So that's where if you're part of like, I don't know, some three-letter agency, you're part of the DoD, you have your own cloud environment that it's not touched by anyone else. That's the private cloud. And then we have the community cloud. So community cloud is still public resources, but it's shared cost. So I'm an Azure. I know Azure very well. So with Azure, we have subscriptions. So our subscriptions kind of dictate, our governance, policy we apply, whatever, and the cost. So a single subscription may have like 5 VMs that cost me 10 grand a month, right? Well, if I'm doing research, let's say I got a federal grant. I work at Harvard and MIT and Princeton, all got the same federal grant. We're all working on the same research. So we say, hey, instead of us having individual cloud costs, let's just all get under one subscription, budget it out to say Harvard has to pay 6 grand, Princeton pays 4 grand, and now we have this community of cost, right? So it's shared costs. Local government does this sometimes, where maybe the city, I'm from Chandler, Arizona, so the city of Chandler says, hey, our budget for IT is $1 million when it comes to cloud infrastructure. So fire department, police department, whatever, public city works, water, whatever the case, we're going to give you a budget and your department's going to share that cost, right? That's the community cloud. And then last, we're going to have the hybrid cloud. So this is just a combination of any of these and plus on-prem. So we could have a hybrid cloud solution that does on-prem plus the public cloud. So maybe this could be something like where we have Active Directory, right, on-prem, and we're doing an AD sync to Entra ID that allows like Microsoft Intune to manage local users on Active Directory, where that's always going to be the source of truth, and that's going to be, local domain controllers, right, that have local users on-prem that we sync up to our public cloud instance or tenant. Now, that's one solution for hybrid cloud, but it could be a private and public cloud that you have in your environment, whatever the case may be. So that's hybrid cloud. So that's our deployment models. Now, service models. This is a little different. So we understand the different deployment models. So how your organization's going to put resources in the cloud, right? We're going to go to the public cloud, whatever the case may be. So now the service models we have. So we have 3 major service models. One is infrastructure as a service, one is platform as a service, and one is software as a service. So remember, the business need for the cloud was to take what we were doing in that data center and moving it up to save us costs. So with that comes these different service models. Remember, it's a business need. So if infrastructure as a service, the best way to describe this is your data center in the cloud. So when we talk about service models, really what we're describing is the customer responsibility and the cloud service provider's responsibility. So when I want to do infrastructure as code, that typically means that I'm going to deploy my own VMs, I'm going to provide my own OS, and I'm going to manage as much as I can. So let me actually make a different color here. So customer responsibility will be green, and the CSP responsibility, the cloud service provider responsibility, will be blue. Now, depending on what cloud provider you're going with, Azure, AWS, Google Cloud, they're going to have different what's called response ability matrices. They're going to describe the different responsibilities associated with these service models. They differ a little bit, but for the most part, they're pretty much the same. The responsibility matrices by all the major cloud providers. So let me actually type this out because I know I'm going to get comments on my handwriting shit. So, infrastructure as a service. Well, no, and fuck it. It'll be fine. So, with infrastructure as a service, this is us deploying our own VMs. So, what's our customer responsibility? It's going to be our responsibility to provide the OS. It's going to be our responsibility to provide the middleware. The middleware being like our frameworks that we need to deploy applications on, like the .NET framework for like Windows, right? Our IAM is going to be on us, our identity access management, user accounts, permissions, things like that. The security. So if I deploy a VM in the cloud and I make it public and I enable Telnet and a hacker gets in my VM and runs up a cloud cost, guess what? That cost is on me, okay? So The OS, the middleware, the IAM, the security, that's all my customer responsibility. There's a longer list that goes along with this, but it's not too important. The cloud service provider responsibility. So the cloud provider is still going to power on your data center. It's still going to provide that console connection, so like that Azure portal you saw me go into, and physical security, because they are still responsible for someone not breaking into that cloud data center. Now, with platform as a service is there. Let's say something I guess I should add in here, like if you're developing an application, all the applications you develop is your responsibility as well. So you can't host a web server in Azure on your own VM and then say, hey, Azure, can you help me with this issue I'm having on my web application? Users are having this issue. They're going to be like, no, like it's not, like they won't help you with that, right? Your developer has to do that. Okay. Now, platform as a service. Now, imagine you just want to deploy code. You just want the ability to deploy applications quickly. That's platform as a service. You want to deploy, you want to develop in your local environment, push to a GitHub repo, and have some platform as a service take and launch your application for you. Without having to worry about the OS, the middleware, and any of the cybersecurity. We don't want to patch it, right? We don't want to patch the underlying server there. That's platform as a service. So the customer responsibility here is the application, the actual development, the actual application you're making, and of course the IAM. Because at some level, you're going to have some sort of like platform as a service console, like you do this in Azure, and you're going to have to say, oh, hey, only this user can sync my platform as a service to my GitHub repo, right? And then everything else is on the CSP. So the cybersecurity, the middleware, the like database if you have it, right? If you're like, serverless architecture. And then of course, again, the physical security and the power for whatever cloud data center is powering that platform as a service. And then finally, software as a service, where pretty much your only responsibility is just to manage the application they're delivering you. So this is Gmail, this is Google Drive, this is Office 365, right? Where you have Teams, Outlook, PowerPoint, all these different services at your disposal from the web. The only thing you have to worry about is IAM. Just saying, hey, what users get access to our Office 365 suite? So they get Teams and Outlook and any other Microsoft suite of applications, okay? And then everything else is on the cloud provider. So the OS, the application, the middleware, the cyber, the physical security, the power, and databases, whatever. Pretty much the full stack they're responsible for, the cloud service provider. All right, awesome. So that is a really basic intro to the cloud. Let me now share my screen again and get back to our slides. Make sure I didn't miss anything. All right, deployment models, public. So public cloud is a cloud infrastructure provision for open use by general public. A private cloud is a cloud infrastructure operated solely for a single organization. It can be managed internally or by a third party and hosted either internally or externally. So like I said, like the Gov Cloud, or this could be something that you host, right? Because the Gov Cloud would still be like Azure Gov Cloud, but it's private for you, or you could build your own little private cloud. All right, hybrid. So a hybrid cloud combines two or more distinct cloud infrastructures. Service model, infrastructure as a service. So infrastructure as a service provides virtualized computing resources over the internet. And again, you're responsible for the operating system, middleware, and applications. Platform as a service that provides customers with a platform, including hardware, software, and infrastructure, where you can just deploy your applications and your runtime environments and whatever you're developing. Software as a service, where applications are hosted by that third party. So again, it's like Office 365. Okay, and then things we get with the cloud, scalability. So scalability is the capability of a system to handle a growing amount of work or its potential to accommodate growth. So a vertical scalability, something I'll define real quick here because I don't want to be too long-winded, is when essentially we take a single node and scale up its resources. We add more storage, more compute, more memory, more cores. With horizontal scalability, this is where we pool nodes together for a single purpose. So instead of us scaling up a single VM or a container, we pool together hundreds of containers to service a single application. Okay, and then elasticity. So elasticity is the ability of a cloud environment to automatically scale resources up and down in response to changes in demand. So think of the elasticity as, hey, I know Azure, AWS, and Google Cloud can scale, but which one does it the best for me? Which one has the best automated ability to be elastic, at what speed and at what cost? So elasticity is kind of like the, I know we're scalable, but how, right? And how well do we do it? Okay, multi-tenancy. So multi-tenancy is a cloud architecture where multiple customers or tenants share the same physical infrastructure. What I talked about with the public cloud. All right, let's do our quiz and then we'll take another break. So we're at domain 1.3.1. Go to our quizzes. All right. So question 1. In a private cloud deployment model, who is typically responsible for managing the infrastructure? See, A, B, and C are an answer though, because like Azure Gov Cloud is like they manage the infrastructure. A third-party hosting company could also do a private cloud, so you could have like a VPS kind of, virtual private server, which is not the cloud, I know, but that that would still be a third party. But I think what they're trying to get here is that the private cloud, that's you, right? And that's good for the test, right? To kind of understand what a CompTIA is asking it. So this is going to be the organization's IT department. All right, question 2. Which of the following is a characteristic of infrastructure as a service? So the service provider does not manage the operating system. Users are responsible for managing underlying hardware. That's not true. Remember, cloud data centers, the cloud provider manages that data center. So replacing servers, racking, stacking. Provides a platform. It's going to be D, because this is describing PaaS. Users can provision and manage virtual machines and storage resources. Remember, that's where you're bringing your own OS and managing pretty much everything besides the hardware and like power, physical security. Question 3. Which of the following best describes the concept of elasticity in cloud computing? Let's see here. The ability to increase storage capacity by adding more hard drives. No, that's like vertical scalability. The use of multiple data centers. That's like high availability, that which we didn't talk about, but that C describes high availability. The ability to support multiple users on the same physical infrastructure. No, not necessarily. We're going to go with B. The capability to automatically scale resources up and down based on demand. Question 4. Which of the following cloud deployment models allows an organization to leverage both public and private cloud resources while maintaining data and applications in separate environments? So they have public and private. So it's going to be hybrid, right? That's combining the two. Question 5. Which of the following is an advantage of using software as a service over traditional software deployment? So, I mean, really the advantage they're trying to get at here is just that you don't have to manage anything. So maybe it's more cost effective to just, buy an application than having an on-staff development company or developers do it for you. So, yeah, C. We'll go with C. That's the best answer. The software is accessed over the internet, eliminating the need for local installations. All right, last question. We're trying to get 100. What is the primary benefit of multi-tenancy in a cloud environment? I think they're trying to get through like the cost savings, right? Because we don't have a dedicated server. It doesn't increase the complexity at all for us, right? And increasing complexity would not be a benefit anyways. So, that's not a good answer. It doesn't isolate. So we're going to go with cost savings through shared infrastructure and resource utilization. All right, awesome. Another 100%. Let's go, guys. So I'm gonna put another 10 minutes on the screen here. I want to rest my voice a little bit, and then we'll come back around like 8:15 ish.